Welcome back to the Deep Dive. Today we are tackling something that sits, right at the very heart of the whole AI dream.
It really does.
For decades we've had this promise, this idea of computers that don't just store data, but can actually think.
That's the holy grail, isn't it? We want a machine that can reason, that can investigate and answer a question based on what it knows, not just, spit back a Wikipedia page.
Exactly. It's the difference between a search engine finding a document with the word John in it and an AI detective looking at all these scattered clues. John is American. There are missiles here. Selling weapons is a crime. And actually connecting those dots to say, aha, John is a criminal.
We're moving from information retrieval to information inference. And to understand how that magic trick actually works, we're doing a deep dive into Chapter 9 of one of the definitive texts on artificial intelligence. We're looking at inference and first-order logic.
Okay, first-order logic.
Yeah.
That sounds a little intimidating. We've talked about propositional logic before, and that was the world of simple, true, or false. It is raining is true. Simple.
Simple, clean, but yeah, kind of limited. The real world isn't made of simple sentences. It's made of things, objects, people, relationships. Propositional logic is like a language with no nouns or verbs. First-order logic gives us those tools. It lets us say things like John loves Mary or the King of France is greedy. It's a much richer way to represent the world.
So first-order logic is the language. Today we're talking about the engine that processes it. This is the machinery under the hood of expert systems, logic programming, even the stuff NASA uses.
Precisely. It's all about how we mechanize the process of proof.
So let's start with what the source material calls the old way, propositionalization. It sounds fancy, but it starts with a really classic example, this folkloric axiom.
All greedy kings are evil.
Right. So we feed that rule into the computer. And let's say our database is full of people. We have John, Richard, Bill, maybe thousands of others. How does the old way handle this?
Well, the brute force method propositionalization, it uses something called universal instantiation. Basically, the computer looks at that general rule, all greedy kings are evil, and it says, I can't handle lovely. I need specifics.
It doesn't like generalizations.
It hates them. So it takes that rule and it just copies it for every single person in the database.
Wait, for everyone?
Everyone. It writes, if John is a greedy king, John is evil. If Richard is a greedy king, Richard is evil. If Bill is a greedy king.
Hold on. If I've got a database with 1 million people in it and maybe 10 rules like this, doesn't that just explode the system?
You've just hit the nail on the head. That's the efficiency nightmare. You get this massive data explosion. The computer just ends up drowning in millions of irrelevant sentences.
That seems unbelievably inefficient. But it gets worse, right? Because not everything's a universal rule. Sometimes you have these existential rules, like there exists a crown on someone's head.
Right. There exists an X. And this is where a computer gets really tricky. It can't handle that kind of ambiguity. If you tell it someone has the crown, it panics. It needs a name. It needs a handle for that someone.
Doesn't like ghosts in the machine.
Exactly. So logic invented a fix. We create a placeholder name for that unknown thing. We call this a Skolem constant.
A Skolem constant?
Yeah, think of it like a police file for an unidentified suspect. They know a crime happened, they know someone did it, but they don't have a name. So they open a file for John Doe or, case 892.
So the computer goes, okay, I don't know who has the crown, so I'm just going to call him entity C1.
Exactly. Entity C1 is the Skolem constant. The computer doesn't know who or what C1 is, but now it has a concrete symbol it can work with in its equations. It turns a vague maybe into a solid thing.
Okay, so we've got the brute force method, we've got Skolem constants for the unknowns. But then the source material brings up this scenario where the whole thing just completely falls apart. Function symbols.
Oh, yeah. The father of problem.
Right. If I have a rule that says everyone has a father, and I try to use that brute force method.
Well, let's trace it. You generate John is a person. So father of John is a person. But hang on, father of John is now a new person. So the rule applies to him, too. So you generate father of John is a person.
And then father of John.
And you're in an infinite loop. You've broken the computer. The machine will just sit there generating ancestors until the heat death of the universe.
This seems like a pretty major design flaw.
It is, and it connects to a famous theorem by Jacques Herbrand. He proved that if proof exists, you can find it in a finite set of sentences. But the catch is finding which sentences is semi-decidable.
Semi-decidable. That sounds like a lawyer's answer. Maybe.
It basically means if the answer is yes, this is true, the computer will eventually find it and tell you. But if the answer is no, or if it gets lost in that infinite family tree, it might never stop. It'll just spin its wheels forever.
So brute force is out. Too slow, might crash. We need a smarter way. And this leads to the big aha moment in the text, lifting.
Lifting is beautiful. Instead of dragging the logic down to the level of specific names, John, Richard, Bill, Hessley, we lift the reasoning up to handle the patterns, the variables, directly. We use something called generalized modus ponens.
Okay, unpack that. Modus ponens is just if A implies B and you have A, then you get B.
Correct. But generalized modus ponens lets us do that with variables. We don't need to generate a million sentences. We just look for a template match. And the key mechanism for finding that match is called unification.
Unification?
Think of unification like a complex stencil. You have a rule that says, loves X cream, and you have fact, loves John ice cream. Unification is the process of laying that rule over the fact and asking, do these fit?
And the computer sees that if it just swaps X for John, they fit perfectly.
Exactly. That swap, substituting John for X, is called a substitution. The computer finds the most general way to make the two sentences look identical.
But what if the variables clash? The text mentions a specific detail here called standardizing apart.
Right. This is just a bit of housekeeping. Imagine you have two different rules. One says, if you know X, you are smart. And another says, if you eat X, you are full.
Both use X.
But the X in the first rule might be a math problem, and the X in the second is a sandwich. If you try to unify them, the computer might get confused and think X is the same thing. Wait, did you get the math problem?
So standardizing apart is just giving them unique name tags, like I were 1 and by 17.
Exactly. It prevents these accidental logic collisions.
Okay, so we've got the machinery, we have unification, we have lifting.
Yeah.
And now let's talk about how the engine actually drives. The source material divides this into two main approaches, forward chaining and backward chaining.
The forward engine and the backward engine.
Let's start with forward chaining. This is described as data-driven.
Yeah. In forward chaining, you start with what you know, the facts on the ground, and you let those facts trigger rules to discover new facts. You just keep going until you find what you're looking for.
There's a classic case study used to teach this. It involves a Colonel West and some shady missile deals.
The crime example. It's a great little logic puzzle. So the facts are, you have a country, No-No. No-No is an enemy of America. No-No has missiles. All of No-No's missiles were sold to it by Colonel West. And West is an American.
And the main rule in the system is that it's a crime for an American to sell weapons to hostile nations.
So imagine the forward chaining engine turning on. It looks at the pile of facts. It sees No-No has missiles. It also sees a rule. Missiles are weapons.
Okay, so it makes an inference.
Right. A new fact is born. No-No has weapons.
I see.
Then it sees No-No is an enemy of America. And a rule, enemies are hostile. So boom, new fact. No-No is a hostile nation.
The net is tightening on West.
Exactly. Now the system has a whole new set of facts. It sees West is American. West sold weapons. He sold them to a hostile nation. All those pieces now fit the template for the crime rule.
And it stamps a new fact into the database. Criminal West.
Case closed. West is going to jail.
Ideally? But there's a catch. If you have a massive system, say a corporate database, with millions of facts, checking every rule against every new fact every single time, that's incredibly slow.
You'd be recalculating No-No has weapons 1,000 times a second. It's not sustainable.
So what's the fix?
That's why we use something called the re-algorithm. It's a clever efficiency hack. Think of it like a smart office manager who keeps a file on every project. When a new piece of info comes in, say West is American, the manager doesn't recheck every file in the building.
Did they just check the files that were waiting for that specific piece of information?
Exactly. It caches the partial matches. It remembers, hey, I have this rule that's half triggered. I just need one more piece. When that piece arrives, it fires instantly. This is what made systems like XCON possible.
XCON?
It was a massive expert system from the 80s that configured computers. It had thousands of rules. Without it would have been way too slow to be useful. This is real-world stuff.
Okay, so that's data-driven. But what if we start from the other end? What if I don't care about No-No or missiles? I just have one very specific question. Is Colonel West a criminal?
Then you need the backward engine. This is goal-driven. You start with the question and work backward.
So the computer asks, okay, to prove West is a criminal, what do I need?
I need to prove he is American and he has sold weapons and the buyer was hostile. It takes that big question and breaks it down into sub-goals. Then it goes hunting for those specific answers.
This feels much more focused.
It is. And this is the whole foundation of Prolog, which is probably the most famous logic programming language ever. Its philosophy is algorithm, logic plus control.
Logic plus control.
The logic is the facts you give it. The control is how Prolog searches through them. And it uses a depth-first search. It picks one path, is he American, and dives all the way down to try and prove it. If it hits a dead end, it backs up and tries the next path.
But there's a trap here too, right?
Yeah.
The text mentions that if you're not careful, Prolog can kind of chase its own tail.
The infinite loop again. It's because Prolog is stubborn. It follows the rules in the exact order you write them. Imagine you have a rule for getting from A to Z that says to get from A to Z, first go from A to Y.
Right.
But the rule for getting to Y says to get to Y, first go back to A.
So it just goes A to Y to A to Y, forever.
Exactly. It never stops to check if the path is actually making progress. It just follows the instructions blindly right into the abyss.
Prolog also has this really interesting quirk, the closed world assumption. That sounds like a sci-fi novel.
It's a philosophical stance, really. Prolog assumes that its database is the entire universe. If it cannot prove something is true from the facts it has, it just assumes it's false.
So if I don't explicitly tell the computer I have a sister,
Then you don't have a sister. As far as Prolog is concerned, in the real world, not knowing something just means you don't know. In Prolog, absence of proof is proof of absence.
which is fine for a flight schedule. If the flight isn't listed, it doesn't exist.
Yeah.
But maybe not for solving a murder. So we have forward chaining for data dumps, backward chaining for specific queries. But the source material introduces one final method. You called this the nuclear option.
Resolution.
So why the nuclear option? Is the other stuff not good enough?
Forward and backward chaining are great for business rules. If score is over 700, approve the loan. Simple stuff. But they crumble when things get ambiguous. They crumble when you have or are.
Or are. Like either Jack or Curiosity killed the cat.
Exactly. If I tell you either Jack or Curiosity did it, and then I say Jack didn't do it, you immediately know Curiosity is the killer. But standard chaining struggles with that or are. It doesn't know which path to follow. Resolution is designed to crush that kind of ambiguity.
And to use it, we first have to flatten everything into a special format. Conjunctive normal form or CNF.
Yes, CNF is the great equalizer. It takes all your complex logic with ifs, thens, ands, ors, and breaks it all down into a simple string of clauses connected by and-ds.
And it brings back our friend Skolomization, but with a twist.
Right. Remember the Skolem constant, entity C1? Well, what if I say everyone loves someone? The person you love depends on who you are. John loves Mary, Bill loves Susan. I can't just replace someone with one name like C1 because it's not the same person for everyone.
So the constant doesn't work because the someone changes for each person.
Exactly. So we use the Skolem function. We say the person you love is a function of you, $5. It's like saying everyone have a shadow. The shadow belongs to you. It's unique to you. The logic creates a personalized entity for every $6.
That's clever. So we get everything into CNF. How does the resolution rule actually work? You called it smashing earlier.
It really is a smashing process. The rule is deceptively simple. If you have one clause that says tires tallers and another that says not der tallers, you can smash them together.
Because tires and not tellers are total opposites.
Right. They cancel each other out, they resolve, and you're left with targer dollars.
It's almost like algebraic cancellation.
It is. And this leads to the most dramatic way to prove anything, proof by contradiction.
Okay, walk me through this with the cat example from the text.
Yeah.
We want to prove that Curiosity killed the cat.
Okay. The facts are, 1, Jack loves all animals. 2, anyone who kills an animal is loved by no one. 3, either Jack or Curiosity killed Tuna the cat. Our goal. Prove Curiosity is the killer.
So how does resolution handle this?
It starts by being contrary. It assumes the exact opposite of what we want to prove. It says, okay, let's pretend Curiosity did not kill the cat.
It adds a lie to the universe.
It adds that lie to the database. Now the dominoes start to fall. We have the rule, either Jack or Curiosity killed the cat. We combine that with our new lie, Curiosity didn't do it. Smash them together, what's left?
Jack must have killed the cat.
Right, so now we know Jack is the killer. But look at rule 2. Anyone who kills an animal is loved by no one. Since Jack killed the cat, an animal, Jack is now loved by no one.
It's a tragic figure.
Indeed. But wait, we have fact 1. Jack loves all animals. And buried in the logic is this idea that if you love something, you are, in some sense, loved back. The detailed proof gets complicated, but it boils down to this. We end up with Jack is loved, and Jack is loved by no one.
That's a direct contradiction. You can't be both.
Exactly. The logic engine hears a loud screeching noise. The universe has broken. We have produced an empty clause, a pure contradiction, and because the universe broke, we know our starting assumption must have been wrong.
The assumption that curiosity didn't do it. That was the lie.
Therefore, curiosity did kill the cat.
It's basically backing the logic into a corner until it has no choice but to admit the truth.
That's exactly what resolution is. It is refutation complete. If a set of sentences is unsatisfiable, resolution will find the contradiction. It's a logical steamroller.
Before we wrap, I want to touch on one last technical headache: equality. The source says standard logic is actually kind of dumb about the equal sign.
It is. It doesn't intuitively know that if 6 Eccles is a thyler, then the father of 6 Eccles is the same person as the father of Yao. To the computer, they're just different symbols.
So how do you fix that?
You give it extra rules. One is called demodulation. That's for simplification. If you know 6 plus Zeller equals Axel, you can tell the computer, hey, whenever you see x plus 0, just cross it out and write x.
And the other one, paramodulation.
That's the heavy hitter. It allows substituting equals for equals inside complex statements. It's what ensures that if we prove 2 things are identical, we can swap them anywhere without breaking our chain of evidence.
So we've gone from these simple lists of names all the way to this nuclear option of resolution. But I have to ask, does anyone actually use this? Or is it just for solving riddles about cats and kings?
Oh, it's absolutely used. And the stakes are a lot higher than a cat. Remember, I called it the nuclear option. That's because you use resolution when you need to be 100% sure. Think about hardware verification.
Like for computer chips.
Exactly. When Intel or AMD designs a new CPU, they're packing billions of transistors on a chip. If they make one tiny mistake in the logic gates, the chip might calculate 2 plus 2 equals 5 under some super rare condition. They can't just test every possibility, they need to prove it.
They use this kind of logic to prove the chip actually works as designed.
Yes. They use these theorem provers to mathematically verify that the design matches the specification. Same thing at places like NASA. If you're sending a probe to Europa, you can't just patch the code if it crashes. You need a mathematical proof that the code will execute correctly.
So inference and first-order logic is kind of the safety net for our whole digital world.
It really is the bedrock of certainty in computing.
But, and here's where it gets really interesting, the source material ends with a bit of a provocative thought. It brings up Gödel's incompleteness theorem.
Yes, this is the ultimate reality check. Just when we think we've built the perfect logic machine, Kurt Gödel walks in and kind of breaks it. He proved that in any logical system powerful enough to do basic math, there will always be statements that are true, but that cannot be proved within that system.
True statements that can't be proved.
It's a mind-bending concept. It means no matter how powerful our AI gets, no matter how perfect our inference engines are, resolution, prologue, all of it, there will always be truths that are beyond its ability to mechanically prove.
So if we're building AI to discover the ultimate truth of the universe,
there are some truths it might never be able to reach. It will just stare at them, unable to say yes or no.
that is a humbling thought to end on. We built the perfect engine, only to find out the road goes on forever. Well, thank you for helping us unpack all this logic today.
My pleasure. It's a fascinating world.
And thank you for listening to The Deep Dive. Go out there, check your premises, and we'll see you next time.